Hi, my name is Saket Kenjale, and in today's video, we're going to be continuing section 1.1, review of functions. And so in our last video, we left off with using mathematical operators to combine functions. So we added, subtracted, multiplied, and divided two functions together. And so we're going to start off this video with composite functions. And this is when you take a function of a function. Now let's take a look at this note over here. Consider the function f with domain A and range B, and the function g with domain D and range E. If B is a subset of D, then the composite function g of f of x is the function with domain A such that g of f of x is equal to g of f of x, where f of x is inside of the g of x function. And so when it says B is a subset of D, it means that all the elements of B are in D. So now let's take a look at an example problem. So it says consider the functions f of x is equal to x squared plus 1 and g of x is equal to 1 over x. And so it's asking us to find g of f of x and state its domain and range. So again, we could write this as g of f of x, like over here. And then we could see that g of x is equal to x. And so if we substitute in f of x for x, we are going to get 1 over f of x. And then if we substitute in f of x for what its value is, we get 1 over x squared plus 1. So this is our g of f of x. And so for the domain, there's no discontinuity in this function. There's no undefined values, so it goes from negative infinity to infinity, all real numbers. And for the range, if you notice that, so here, let's take a look at this. So we see that there's an x squared in this denominator, and if we get infinitely big, if we go infinitely big to infinity, then this over here will basically be 1 over infinity, which is equal to 0. And if we were to go all the way to negative infinity, let's say, it'll be the same thing, because negative infinity squared is just infinity. So this will have the same result. It will go all the way to 0. So basically what this is saying is that as the function increases or decreases, it gets closer to 0. And at x is equal to 0, we see that the function will be 1 over 1, which is just 1. So in this case, the interval goes from 0 to 1. Sorry, 0 to 1, and this is a closed bracket. Notice how we're not including 0, because when we go to infinity, we never actually get to 0, but it's extremely close to 0, so we just say it's 0, but it's not including 0. So this is our range, and this is our domain. Now let's move on to part B. So it says evaluate g of f of x of 4 and g of f of x of negative 1/2. So we have g of f of x, which is 1 over x squared plus 1. And now we just have to substitute in 4 and substitute negative 1/2 later to find these values. So if we were to substitute in 4 for x, we would get 1 over 4 squared plus 1, which is equal to 1 over 16 plus 1, which is 17. So we get 1 over 17. For negative 1/2, well, it would be 1 over negative 1/2 squared plus 1, which is equal to 1 over 1/4 plus 1, which is then equal to 1 over 5/4, which is equal to 4/5. Now it's asking us to solve for f of g of x. So in this case we had g of f of x, and now we have to solve for f of g of x. And so we have the function f of x, and we substitute x in for g of x. So we know that f of x is x squared plus 1. And so if we were to substitute in g of x, which is 1 over x into x, basically, we would get 1 over x squared plus 1. So this is equal to our f of g of x function. And now let's solve for the domain and the range. So for the domain, we could see that it cannot be 0 because it would give us an undefined value, and all other numbers work, so it will go from negative infinity to 0, and from 0 to infinity. For the range, it's a little bit complicated, but it's not too bad. So let's say that 1 over x squared plus 1 is equal to y. So let's set f of g of x equal to y. So this is equal to this. I'm going to erase this just for space, but I hope you remember that. If we were to solve, or if we were to isolate for x, then we would know what y values are possible in the function and what y values are allowed in the function, and then we could solve for the range. So I'm going to start by subtracting 1, and so we're going to get 1 over x squared is equal to y minus 1. Now we're going to take the square root on both sides, so we're going to get 1 over x is equal to the square root of y minus 1. And so, well, if we were to solve for x itself, then we will multiply x on this side and divide by the square root of y minus 1. And so x will become equal to, and sorry, by the way, when you take the square root, you have to, it's positive or negative. So it would be positive or negative y minus square root of y minus 1. So positive, negative over here. And so x will be equal to 1 over the square root of y minus 1. I'm sorry if I'm getting a little bit messy here. I don't have too much space, but we'll work with it. So now we have x isolated, and so now we can see what the range is according to what y values are possible. So in this case, y is under a radical, so this term right here cannot be less than 0, otherwise it will be an imaginary number because you can have a negative radical. So we know that has to be 1 or greater. So that is why the range, goes from 1 to infinity. So since this value is in the denominator, it cannot be equal to 0, so therefore we cannot include 1 in our interval, so it's going to be an open interval from 1 to infinity. Now we are asked to find f of g of 4 and f of g of negative 1/2. So again, this is our f of g of x function, so we will write it down here, 1 over x squared plus 1. And so if we were to substitute this in for 4, we would get 1 over 16, basically, because 1 over 4 squared is 1 over 16. plus 1 is equal to 16 over 16. And so, here. So the answer is 17 over 16. And so for negative 1/2, it would be 1 over negative 1/2 squared plus 1. And we would get 1 over 1/4. Yeah, 1 over 1/4 plus 1. And that's equal to 4 plus 1, or 5. So these are answers to part D. Now we're going to talk about symmetry of functions. So in this video, we're not going to be talking about symmetry over the x-axis, but we will be talking about symmetry over the y-axis and symmetry over the origin. And so for symmetry over the y-axis, if the point x, comma y is on the graph, then the point negative x, comma y is also on that graph. So f of negative x is equal to f of x. And we call this an even function. So functions that are symmetric over the y-axis are known as even functions, and this is an example of an even function. And we could see that using this logic that there should also be a negative x comma y point on this graph. Let's just plug in a random point. So let's say that this is 3, 3. Right? So according to this logic, this is saying that since this graph is symmetric over the y-axis, there should also be a point negative 3, 3. And as you can see, there actually is. So this proves this to be true. And then now we're going to talk about symmetry over the origin. And for symmetry over the origin, if the point x comma y is on the graph, then the point negative x comma negative y is also on that graph. So f of negative x is equal to negative f of x. And we call this an odd function. So this is an example of an odd function. And let's pick this point over here. We'll call this negative 3, 3. So according to this logic, there must be a point on this graph that is 3, negative 3. And we can see that there is a point just like that over here. So now we're going to go over an example problem. So it says to determine whether each of the following functions are even, odd, or neither. And I want you to keep in mind that there are functions that are neither even or odd, so it goes in this neither category. So let's substitute in x for negative x for part A, and we would get negative 5 times negative x to the power of 4 plus 7 times negative x squared minus 2. And so if we were to simplify that, we would get negative 5x to the 4th plus 7x squared minus 2. And this is the exact same thing as our original function. So this means that this is an even function, because even functions state that if you substitute in x for negative x, then you will just get the same function. So that's how it worked, and that's why it's even. So let's work on number 2. So we put negative x in, it will become 2 times negative x to the power of 5 minus 4 times negative x plus 5. And simplifying that, we get negative 2x to the power of 5 plus 4x plus 5. And so we are not getting the same thing as our original function, but if you're not getting that, then a good thing to do is to factor out a 1 just to make sure that this is not an odd function, because an odd function is the negative of the original function. So doing that, we would get 2x to the power of 5 minus 4x minus 5. And this again is not the same thing as our original function. So this does not work, so this is neither. And let's move on to the last problem. And so if we were to plug in or substitute in x for negative x, that would equal negative 3x over negative x squared plus 1, which is equal to negative 3x over x squared plus 1. And then if we were to factor out a negative 1, we would get, inside, we would get 3x over x squared plus 1. And this is the exact same thing as our original function, and then there's a negative 1 outside of it. So that means that this is an odd function. The last topic that we're going to talk about in section 1.1 review of functions is the absolute value function. And so the absolute value function is defined as a piecewise function, and specifically the negative function is at the top where x is less than 0, and then the regular function is at the bottom where x is greater than or equal to 0. And an important thing to know is that the absolute value functions are symmetric over the y-axis without any translations. Like the raw f of x is equal to the absolute value of x. And in this case, your graph would look something like this. It would just be v. And so our last example problem for this section 1.1 is find the domain and range of the function 2x minus, so 2 absolute value x minus 3 plus 4. And so when finding the domain, it is very easy. It is just all real numbers. So it goes from negative infinity to infinity, because the absolute value functions are continuous and there are no breaks or stops, or it always just goes all the way to the right, all the way to the left, and it's continuous. So yeah, all real numbers. The range, we could tell just by looking at these translations. So in this regular absolute value function, we know that the lowest point is at 0, 0, and the y value is equal to 0. Then it goes all the way up to infinity. But in this case, we got a couple of translations and whatnot. So if we were to graph this, so we notice that it goes to the right 3 units and it goes up 4 units. So this lowest point is at 4, and then it opens up. It's kind of squeezed in because of this 2 in the front. So it's going to look something like this. And that goes up there. You get it. So the lowest point is at 4. And then it goes all the way to infinity. So this is it for section 1.1 review of functions. It was split into 3 parts, and I know it was really long. I plan on cutting down the content, or at least making the content go by quicker, so these videos are shorter and it's easier to understand. But nonetheless, I hope you find these videos helpful, and I will see you in section 1.2, which is basic classes of functions.